Today, we're going to talk about vectors. As an example, we start with displacement. Supposing we have an object which starts at this point A and ends up at this point B, but it travels from A to B along some curved path. The length of this path is the distance traveled. But the displacement of the object is the change in its position. It is represented by an arrow. We start the arrow, the tail of the arrow at the starting point, and the tip of the arrow is at the ending point. So this arrow represents the change in the position of the object. Now, when we are talking about the change in the position, we don't care about what happened in between. We don't care about how far it traveled. You notice that this arrow has a length, which is the magnitude of the displacement, and it has a certain direction. Let's give this displacement a name. We'll call it A. To indicate that this is a vector, meaning it has a magnitude and a direction, we put a small arrow on top of it. Notice that this small arrow doesn't have to point in the direction of the displacement. It is to indicate that A is a vector. Let's look at 2 or 3 more examples. Supposing I ask a student to displace a book by 1 meter north. So here is a book, and let's say the student is asked to displace it 1 meter north. One way to do it is to take the book straight up in the northern direction by 1 meter. So the student has performed a displacement of 1 meter. There is another possibility. The student could have taken the book all over the school and finally brought it and put it in the final position, which is 1 meter north of the initial position. This is also a displacement 1 meter north. Supposing I ask another student to displace his book by 1 meter north. Now this student could have gone to the edge of the galaxy and come back and place the book 1 meter north of the starting point. So this is also a displacement 1 meter north. Notice that the 2 displacements start at different points, end at different points, but both are 1 meter north displacements. So if I call this displacement vector B, then this is also vector B. Both represent the same displacement 1 meter north. So the first lesson we learn is that 2 vectors of the same length pointing in the same direction are equal to each other. Another way of saying it is, if I have a vector here and I slide the vector without moving its direction and without changing its magnitude and bring it here, I have not changed the vector. If this is vector C, this is also vector C. So the first lesson we learn about vectors is the starting and the ending point are not so important. It is the change that is important. And the change in the position is called the displacement. Let's go back to our object. It started at point A. It ended at point B, having gone through some complicated route and arrived here. Now we noted that the displacement was this vector starting at A and ending at B, the tail of the arrow at A, the tip of the arrow at B, and this displacement, we gave it a name, we called it A. Having arrived at B, supposing the object goes to C, another point, along some other path, some other complicated path, and arrives at C. In other words, the object has undergone a second displacement given by this different vector. Displacement is a vector because it has a magnitude and a direction. Let's call the second displacement B. Now if you look at the overall path, I started at A and the object went through this complicated route, arrived at B and went further through this another complicated route and arrived at C. So the total displacement is starting at A and ending at C. So the net displacement is this vector. Let's give it a name. We'll call it C. So now we'd like to write an equation that says vector C is the result of vector A followed by vector B. You see, first we perform a displacement from A to B and then a displacement from B to C. The net displacement or the resultant displacement. So what is C called? It's called the resultant. The resultant is the word we use to mean the result of displacing by A followed by displacement of B. The resultant of A followed by B, so we need a symbol here for A followed by B. Now we can invent our own symbol. We can perhaps put a star out there. So star represents displacement A followed by displacement B. Alternately, we could have put a smiley face, right? Smiley represents one displacement followed by another displacement. But our ancestors, that is the engineers and the scientists who did this first, they chose the symbol plus. So in the context of vectors, plus does not represent our ordinary addition. A might, for example, be 7 meters long in that direction and B might be 6 meters long in this direction. The vector sum of the two, which is C, as you can see from the drawing, is not 13 meters long. So you do not perform ordinary addition when you are adding vectors. So the plus in this context represents something else altogether. So in the context of vectors, plus represents vector addition. And what does that mean? It means the following. Let's say we have two vectors, vector A and someone gives you vector B. So this is A and this is B. And you are asked to find A plus B. So what you should do is think of these as displacements. Imagine an object starts at the tail of A and after going all over the place finally arrives at the tip of A. So it has undergone the displacement A. Now that has to be followed by displacement B. Now remember, we are allowed to slide vectors. So what we are going to do is slide this vector over here so that vector B is a displacement that follows vector A. As long as you don't change the magnitude and the direction, the vector doesn't change. So if this is B, this is also B. So now we have displacement A, I arrive here, and from here perform displacement B, and the resultant, which is A plus B, is the displacement C, which starts at the tail of A and ends at the tip of B. So this is C. So C is equal to A plus B. So in the context of vectors, the plus represents the following. When you're asked to add two vectors, the plus represents addition. It's called vector summation or vector addition. In the context of vectors, when you're asked to add two vectors, what do? You slide one of the vectors until its tail is touching the tip of the first vector. Join the tail of the first vector to the tip of the second vector, and that gives you the sum of the two vectors. How do we find the magnitude of C? Well, now we have to use geometry and trigonometry, but before we get to that, please understand this concept first. I want to remind you of something important. For the first time in your lives, you're now coming across a situation where the symbol has different meanings in different contexts. When you have 6 plus 7, in this context it is 13. No. In the context of vectors, plus represents slide the second vector until its tail touches the tip of the first vector, join the tail of the first vector to the tip of the second, and you get the vector, you get a new vector which is said to be the sum of the first two vectors. Now vectors have a property which is similar to addition, which is commutativity. What does commutativity mean? Commutativity means it doesn't matter in which order you add the vectors. A plus B will always be equal to B plus A. Let me prove that. Supposing we have vector A and let's say vector B. So once again, we start with adding A and B. So what should I do? I should slide vector B until its tail is touching vector A. So we have this vector B, and then the sum of the two, A plus B, let's call that C. Let me draw C vector for you. C vector is this vector drawn in yellow color, that is C. Suppose now I complete the parallelogram. A and B form two sides of a parallelogram. Let me complete the parallelogram. If I complete the parallelogram, you can see the following. What is this vector? This vector is B. It has the same length and the same magnitude as B. What is this vector? This is A. This of course is C. Now if you look at the yellow triangle, you can see that B vector, displacement B, starts here, ends here, starts at A, ends at B. And from B you perform A vector, you end up at C. The resulting displacement is C vector. In other words, you can see that B followed by A is also C. So if you compare these two equations, you can see that A plus B is equal to B plus A. Given any two vectors, you can always complete the parallelogram. So right away you see that the order in which you add the vectors doesn't matter. It obeys commutativity, which is one of the properties of ordinary addition. We know that 3 plus 7 is the same as 7 plus 3. It has the same property of commutativity as ordinary addition. It also has the same property of associativity. I will let you convince that for yourself, which is if I add A to the sum, vector sum, remember, of B and C, it's the same as finding the vector sum of A and B, taking that resultant and adding it to C. In other words, when you have 3 or 4 vectors, it doesn't matter in which order you add them. This is called the associative property, which is also a property of ordinary addition. Because it has so many properties similar to ordinary addition, we use the same symbol plus in this context. Now here is the important thing. All vectors, examples, displacement, velocity, momentum, acceleration, force, these are all quantities which have direction as well as magnitude. They all add in the same fashion. They all behave exactly like displacement. So if you understand displacement, you will understand all these vectors. Let me give you an example. Supposing two forces act simultaneously on an object. So here is an object, and let us say someone is pulling it towards the north with a certain force. At the same time, let's say someone is pulling it to the east by another force. Let's say this force, the units of force are newtons. Let's say this force is 10 newtons and this force is also 10 newtons. First thing you need to understand is that these two forces are not equal. Now you might say, look, this is 10, aren't they equal? No. Forces are vectors. These two point in different directions. Therefore, they are different forces. So if I call this force F1, Don't forget to put an arrow on top to indicate it's a vector. And if I call this force F2, then you see F2 vector is not the same as F1. So you cannot call the eastern pointing force as F1. It's F2. Under the action of these two simultaneous forces, in which direction will this object accelerate? So it turns out you have to take the vector sum of the two forces, F1 plus F2. That is, the two forces acting simultaneously is equal to a single force F, which I will now draw. How do I find the vector sum of these two forces? Slide one of the forces, it doesn't matter which one, until its tail is touching the tip of the first one. Join the tail of the first one to the tip of the second one. This yellow arrow is the resulting force F. So what does it mean to say that this F, single force, is equal to the vector sum of these two? It means that the two forces acting simultaneously can be replaced by a single force F. That is the resultant of these two forces acting simultaneously. So we can forget about F1, we can forget about F2, we can concentrate only on F. And if you look at this drawing, this is 10 and this is 10. So from Pythagoras theorem, because this is 90 degrees, why is it 90? Because F1 points north, F2 points east. Because it's a 90-degree right angle triangle, F has a magnitude. How do I write the magnitude of F? You put these two lines. The magnitude is, that is the length of F is, by Pythagoras theorem, root of 10 squared plus 10 squared. That is equal to 10 root 2. So, a 10 root 2 Newton force acting at 45 degrees. How do I know it's 45 degrees? It's a right angle isosceles triangle. So, this is 45 degrees. So, the answer is F1 plus F2 is not 20. It is 10 root 2 units acting at 45 degrees. And therefore, this block will accelerate in this direction. And what will be the acceleration? According to Mr. Newton, you have to take this force 10 root 2 divided by the mass of the object. You will get the magnitude of the acceleration, which is also a vector. That vector will be in the same direction as the force. So this is an example where we add forces. When you add forces, you have to add them vectorially. So in the next video, we'll talk about vector subtraction. So, goodbye for now.